One before I forget. We are now in week 13, folks. We're nearly there. We're about ready to start. Yeah, that's close enough. Welcome back, everyone. So we're on week 13, and the announcements are pretty much all on here already. What is interesting about week 13 is next week we're getting through another examination week. So that takes up Tuesday. We'll have one more day to work on probably section 5.3 on Thursday of that week. Then we'll come back on closed week, which means we can't introduce new information. All we'll be allowed to do is finalize whatever problems we didn't finish on 5.3, and we'll be moving into reviewing for the final exam at that point. So we're pretty close. We have just one more exam to get through, some review for the final exam. And at the moment, here's where we are at now for the announcements. Quiz 7 is a really pivotal quiz because this one's based off optimization. And the problem I'm going to ask on optimization, last section on exam 3, is going to be pretty similar to this one as well. So if you can get through this quiz, understand all the moving parts in there, then you're going to have great success on the same kind of problem in 4.4. But as for the rest of the problems, this is a big section list. If you're curious about reviewing any of these problems whatsoever, when we come back on, let's see, that'll be Thursday's class, the 17th. Just like on the prior exam 1, exam 2, we did a big review on. I'll be happy to spend some time or even all the class time on the 17th reviewing for the third exam. So come prepared with questions, and it'll be a student-directed review just like the other ones. But any other questions at all, folks, at the moment? Okay, maybe last bit of announcements, and then we'll jump back to section 4.6. If you're in the online section, I sent out an email to contact the Pocatello Testing Center to schedule the exam. If you're in the Idaho Falls section, we'll be doing the exam in class on Tuesday, which is weird. It means for those who connect through Zoom, we won't have a Tuesday's class. We'll just be doing our exam on that day. So as you prepare for the final, or not the final exam, as you prepare for exam 3, pay special attention to the exam 3 formula sheet. This will inform what you'll have provided on the real exam, what you need to memorize. Looks like we have some theorems related to setting up exponential growth, exponential decay, some information on differentiating logarithmic functions. Properties of logarithms is a big part of section 3.7, so it's available here. And then everything else is just information in chapter 4. Absolute maximums and minimums, the local maxes and minimums. This is a really important definition about the critical number. A lot of the methods in chapter 4 really just start here. Differentiate, set the derivative to 0, and solve for critical numbers. Then you should expect a problem on the closed interval method. You should expect to potentially use this test and first derivative test, or the concavity test. I'm not going to ask both problems because the exam would be a little bit too long. So I'm either going to ask a problem of find local maxes, local minimums for the first derivative test. This is now section 4.2, or ask you to find out where the curve is concave up, concave down, inflection points through the concavity test. Then the last bit, section 4.4 optimization, essentially quiz 7, is going to use either the second derivative test or the first derivative test, but in that slightly tweaked way. These aren't the tweaked versions, but really the analysis goes the same. You're expecting exactly one critical number, and you use this information to determine if it's the absolute max, absolute minimum. So that's the set of notes. It's pretty wordy than the other ones, less actual formulas, lots of words on there, but it helps direct what we have to do on each one of these kind of problems. And the different versions of the sample exams are just like before. Version 1, textbook problems. So these are mainly odds you can take a look into on the online textbook and WebAssign. Version 2 are the actual lecture notes that we've been running through, but now it's converted into worksheets. So this is a good document. It is 11 pages, but it's a good one to target a specific section, like maybe 3.6, maybe 4.2. This is the same kind of document, except that this one is a little bit different. This is brand new problems. Some of them are a little bit more challenging, but for the sake of extra variety, that's what's going on in the third version there. So just like on the other exams, 3 different versions, and I'm happy to discuss any one of those versions as we do our review on Thursday for questions. Or really anything else. If there's a problem in WebAssign that just seems weird, one was brought to class on our exam 2 review, we could do that again as well. But that's, I think, our full spiel for the announcements. We're finalizing quiz 7, which is really helpful for the third exam. We'll post a quiz 8 as well before we go on to our Thursday's class. But I'll turn it over to you folks for the moment. Any last questions at all about the announcements before we get started? Okay, let's go back to 4.6, working on the antiderivatives. We started this section already, so let's kind of review just to get warmed up on what's going on in this section. We'll say an uppercase function f is an antiderivative of the lowercase function f in green if the derivative of the uppercase function directly equals the lowercase function for all x in a domain. So this color coding we're going to maintain very rigidly throughout the entire notes because the relationship between what is the antiderivative and what is it antiderivative of, the blue and green, is really major. Now we check this out a couple ways. If this is your f of x function, and that's the lowercase f of x, we differentiate this and got 10x power 4 minus 6x plus 2, but that's not equal to this at all. The plus 2 is a little bit off right here. That tells us uppercase f of x is not an antiderivative, but we check this again in a different problem. In part B, if you differentiate x, natural log x minus x, turns out the derivative of that really is the natural log x. So we have a bona fide, legitimate antiderivative. But there's infinitely many antiderivatives. So part C here, we introduce a constant, differentiate that again, and we skip natural log x back again. The only thing new is the derivative of this constant would be effectively 0. So we're back to natural log x, and f is still an antiderivative. But what we did with this information was we realized if we want an antiderivative of f of x, and we want to specify every possible antiderivative that will work, it has to look like this. We have to add on the constant of integration, which represents any real number. And then it just gets wiped out once you differentiate it, making the antiderivative its incorrect form. So that was our warm-up page. The major idea is you differentiate this function and it directly equals another function, you really have an antiderivative. But what example 1 is really all about is this is the check process. It's up to us to come up with f of x all on our own, but whatever we come up with, you can check this really fast now. Just differentiate whatever you provided, and you'll see if it equals f of x or not. So here's where the problems in the notes turned up the heat just a little bit more. We have the same definition before. Theorem 1 tells us that if we find an antiderivative, to get all possible antiderivatives, we add the constant c. We call this the most general antiderivative. And any problem that says find an antiderivative is looking for that, the most general form. Here we took the antiderivative of x power n. We get the exponent 1 higher. We divide by n plus 1, and this is adding the constant. But then this is the example 1 problem. We check this out immediately just by differentiation. We find that the derivative of this, even with that constant c there, it goes to a 0, is really lowercase f of x power n originally. So that took us from one really important formula to the next one. The antiderivative of a 1 over x. This is really weird, and we made a big deal out of it. But this one in the antiderivative is the natural logarithm of the absolute value of x. We even directly cited a theorem. This was from section 3.7 on exam 3. So we get this as an antiderivative. We never checked it, but let's do the check right here. In the check, we'll calculate f prime at x, which means first step, we calculate the derivative of natural log absolute value of x. Absolute value is weird here. If it was just natural log x, we know it's 1 over x. But the theorem over here from the last section says absolute value doesn't matter. It's still 1 over x when we differentiate that. So here's our 1 over x from differentiating natural log absolute value of x. Derivative of any constant, even if it's an arbitrary one like this one, is still 0. So here's the plus 0. Then this equals 1 over x, which is equal to f of x. And our check is complete. The derivative of our answer gives us back the question, and that tells us we have the right antiderivative. We've essentially reversed the whole process of differentiation when we come up with uppercase f of x. I will try that out again on the next set of examples. But any questions at the moment, folks, with what we've got so far? Okay, let's get into some of the more routine exercises that goes along with this topic. Starts off like this. Well, we did parts A and part E because that was a weird enough one to look into right away. And now for the rest of the problems, let's cite the instructions again just for easily visualization. We want the most general antiderivative. But the instructions just say, find the antiderivative of each function. Plug that in just so we have instructions available for us. But maybe I shouldn't have deleted that. We do need the power rule in this problem, so let's cite it again. Power rule says, well, power rule in reverse says, this will probably be our most used formula when it comes up to antiderivatives. Let's cite it this way. If lowercase f of x, let's do the color coding as well. Lowercase f of x is x power n, and critically, n is not equal to -1. When it's equal to -1, that's the 1 over x, x power -1, and it has a very specialized antiderivative. But in all other cases, we can say then uppercase f of x, we're indicating the antiderivative as per the original definitions in these notes, is going to be x to the power 1 higher. So now it goes up n plus 1. We multiply instead of, we divide instead of multiplying by the new power. So 1 over n plus 1. And we add the constant of integration c. So this is our power rule we stated before, when n is not -1. And now over here, we can apply the power rule directly. Here's how it goes though. If you have 1 over x cubed, you wouldn't even want to differentiate this in that format. You're using the quotient rule needlessly. Instead, let's take the 1 over x cubed and call it x power -3. It's not just a good idea, it's a really good idea, because what this tells us is what the actual n value is in the lowercase f of x function. So this will tell us, let me use some color coding here. This right here will tell us what the actual n value is, and informs us on how to get the antiderivative correctly. So on the next line, once we reformat the function in a more appropriate way, we can say f of x equals, include a little bit of space before you write down x because we put a coefficient in front. But usually it's a better idea to manipulate the exponent first. In an antiderivative, power goes up. And in a derivative, the power would have gone down. So we'll get power -2. This feels weird because this is a reversal of directionality. It takes some practice to get used to this. Whatever the new power is, over here, this indicates you divide by it immediately. So divide by -2, we could write that as a -1/2 multiplying if you prefer. Then add a constant. This is really pretty weird. I think it deserves an extra statement. Let's write it down here. For the power rule, if we differentiate, a power rule, notice it really has two formats, whether you're finding an antiderivative or if you're differentiating as normal. And in differentiating, power goes down. But if you're finding the antiderivative, could call that anti-differentiating, but that seems like an abuse of the English language. Let's just call it an antiderivative. Power goes up. with an exclamation mark, because that's the part we're now trying to get used to. And that's why we went from -3 to 1 higher and -2. But if we're not sure on this, the check is a really, really good idea. It's extremely rapid. For leaving the check on the table, then it's as if we're just not looking into the answer sheet essentially when it's right there in front of us. I would encourage you to do the check on every single problem. Although you don't have to show it necessarily. Maybe you did it on scratch paper. Maybe you just looked at it and you did it by mentally just eyeballing it, imagining yourself taking the derivative. Either way you're doing this, definitely take advantage of the check. All you're doing is differentiating f. Here's how it would look. F prime of x means we copy in the leading coefficient, -1/2. Derivative here would mean the power comes down, and the power is a -2. And the new power on x is 1 less because we're differentiating now, -3. This constant just goes away entirely. And when we look into our check, there's a cancellation of the coefficients. -1/2 times -2 is a +1. We really get x power -3. The moment we call this, let's say, y, because the function was stated as a y, our work is done. It tells us in blue that really is the right antiderivative, and we can move on to the next interesting example. But these are tricky. These are good ones to spend a little extra time on just to see how they go. Any questions at all, folks, on running through part B? Okay, so when we do the antiderivative, our power went up. But when we did our check through differentiation, power went back down. So we had power -3. And this is interesting as well. If your function is e to the x, that's like the best derivative in the world. It's also the best antiderivative in the world. We know the derivative of e to the x is e to the x, no matter how many times you differentiate. So this directly implies the antiderivative is e to the x as well. We just have to add on the cost of integration. The check is even faster. The check would be f prime of x. You differentiate e to the x, but that is itself. The derivative of the constant is 0, so we just get e to the x, which is lowercase f of x, and our work is done just immediately. I'm writing the check in orange to make it show as a comment, only to emphasize the answer is what's written in blue, uppercase function f of x. But again, that's kind of nice to have a function like that in differentiation, where wherever direction we're going, the answer is pretty immediate on this one. But part D is worse. Part D requires a formula to cite because you might have noticed differentiating e to the x is a great time. Differentiating 7 power of x is not as fun. This one's a little bit more tricky. It requires a formula. Any questions at all with part C before we take a look into part D? Okay, let's put down a formula just to assist with this one. I have formulas indicated essentially in purple so far, it looks like on example 2. And the formula I want to give is first going to be the differentiation formula. We multiply with, if we differentiate, so d by dx, an exponential function like 7 power of x, what we get is 7 power of x times the natural logarithm of 7. So that's what would happen in this problem if we differentiated it. Sadly, that's not what we want. So we want the antiderivative. But what we can now say is that, let's say it this way. Derivative with respect to x of base b to the x, now just as a general formula, is base b to the x times natural logarithm of b. And so we can say from this, f of x equals b to the x has antiderivative that goes like this. F of x equals, let's take a look at what happens when we differentiate. We get the b to the x times the natural log of b. So if we're reversing this whole thing, it ought to be b to the x divided by natural log b. We're just literally going backwards, add a constant c, and that should be the answer on this one. If we can really make that formula work out in our minds, then part D really wasn't so hard. It just needed that extra formula. Let's do a check on the formula itself. The check would go like this. F prime of x is going to be, well, this is kind of a confusing check when we look at our function f of x. Let's rewrite it. F of x can also be rewritten as 1 over natural log b times b to the power of x plus a constant. We can differentiate on this line in purple, but I think it's harder to see this derivative. If you rewrite it like this, now it's cleaner to see this is the constant multiple rule. 1 over natural log b is just a constant. It's not going to move when we differentiate. So it doesn't budge, it just stays right exactly where it is. Think of it like 5 times x. The derivative of that would keep the 5, x just turns into a 1. Over here, we now differentiate. The derivative of b power of x through this formula looks like this. You get b to the power of x times the natural logarithm of b, and then plus 0 just through differentiating the constant c. Next on our check, oh, that's not quite right. Let me try again. On our check, natural log b right here and natural log b over here in the numerator, they do cancel out. That means this is b to the x. That's the original function, b to the x over here, equals f of x, and this completes the check. That tells us this is a true formula. Let's box it out just to make it feel more important. F of x equals b to the x has this as an antiderivative. We take that information and come back over here with it. Back to the actual problem. Antiderivative of 7 power of x is going to be 7 to the power of x divided by natural log of 7 plus a constant. That's exactly what this was indicating. Really, the only thing we had to change once we had the formula is the fact that base b is 7. We just rewrote a 7 in those two places, and that's the right antiderivative. I feel like a check on this one might be tedious because we did a check on the formula, but the check is so important. Let's try it out one more time. The check is fast. It goes like this. Differentiating this function in this format would give us 7 power of x. Constant multiple rule would say the 7 in the denominator, the natural log 7 in the denominator, doesn't budge, which is analogous to what happened over here. We just didn't separate it out this time. But then once you differentiate 7 power of x, it becomes itself 7 power of x times the natural log of 7. That's through this formula right here. Only difference is replacing base b with a literal 7 would give us the 7 power of x times natural log 7. And my check looks a little funny. Let me fix the format here. What I'm doing on the check, but I forgot to actually write in, this is helpful for the mind, is I'm differentiating uppercase f in this way. So f prime of x, highlighted in yellow, is this. Constant multiple rule is just a natural log 7 copied down. Constant plus c goes to a 0. And so here's the cancellation, much like the one on the right, but in a slightly different algebraic format. We get 7 power of x, which is equal to f of x. So our work is done. It tells us in blue that is the real answer to that antiderivative, 7 power of x. Just similar to this one, the only difference in the antiderivatives is here, if we use that formula, we'd be dividing by the natural log of e, but that's just a 1, so we never had to. Here, we have to. Natural log 7 is not equal to 1. Well, we got through the exponentials, and we've got through the power rule in several different ways. Any questions at all, folks, with parts C or D? Okay, I think we're getting through all the new formulas that we have to discover as well, so that's a nice comfort at the same time. Next batch of problems are a little bit more built up. Now the functions are getting bigger, and we want to find the antiderivative of every one of these terms. But for finding the antiderivative of this, really, we're taking the same process we might have taken if we were differentiating this function. If I was to differentiate this, the quotient rule would never be called. That's because it's really fast to expand and then just divide by x, differentiating the result. Same concept here for the antiderivative, and even a more important concept. because we've never specified how the quotient rule reverses. In fact, textbooks usually never do. They reverse the product rule, and then that's it. The reversal of the product rule is called integration by parts in chapter 6. So to really find the antiderivative of this thing, we need to expand it as much as possible. So let's write that here. Expand. By expanding, what I mean is we'll FOIL in the numerator and then divide all terms by x. So let's rewrite f of x equals, first FOIL method in the numerator, distribute x through for a 3x squared, minus x, distribute the 5 through for a plus 15x, minus 5, it's all divided by x. We then get 3x squared plus 14x minus 5, all divided by x. And like we said, we're going to really literally divide everything by x. Let's show that as another line, just for clarity. 3x squared over x plus 14x over x minus 5 over x. So on the second line, still lowercase f of x, we're just going to simplify now. On the first term, it's a 3x. Second term is a constant 14. And the last term is extremely problematic, especially if we leave it in that format. Here's the problem with that last term. This part has antiderivative involving natural log, absolute value of x. And it's just really hard to see. But if we separate things out a little bit more, it kind of pops out at us. Just rewrite this as a -5 times a 1 over x. And that 1 over x is the one problem in example, I believe, 2 now, where it was a combo break for the power rule being reversed. The reversal of the power rule fails when the power is a -1. Bring x up to the numerator, the new power is -1. So this one has antiderivative natural log absolute value of x right here, just out of nowhere. But once we get through surviving manipulating the function, antiderivative uppercase f of x is really fast at this stage. Here's how it goes. We're going to use the power rule 2 times and then something else right over here. Power rule goes like this. First copy in the 3, go into right x. X in its power, it's currently power 1, but it goes up on the antiderivative, so now it's power 2. Once we get that new power, we have to divide into it, divide by it. So 2 goes down below in that way. So that's 3x squared, or 3/2 x squared. While we're doing this, at the same exact time, you want to do a check as well. But I know that feels weird. We're building a problem, and we're checking the answer simultaneously. The check here on the right, like I mentioned, is something you might be doing on scratch paper, on the far right margin of an exam sheet, or maybe just mentally. For the mental version, just imagine you differentiate this by looking at it. Power 2 will come down, canceling that power 2. New power is 1. So this would just be a 3x. That's what it should be. We're in the right line here. But here's what the check is going to look like in this way. I'm going to put in 3/2 x squared, the first term. Let's just write this in. If we differentiate, it becomes 3/2 times 2 x. And then that simplifies further. But before we go to the simplification on the check, let's keep on going further to next term. So 3x and antiderivative became this. We need a new antiderivative. A volunteers to say, what is the antiderivative of the number 14 that's going to go right here? If we differentiate the constant, it would go to 0. Good call. There's really an x to a power right here. It's x power 0. That power 0 goes up to power 1. You would divide by 1 right here, but that's no change. Really, the idea is any constant you see like this, just throw it into x and you're on your way with that one. So good call, just go 14x. This is an important idea in its own. Antiderivative of a constant is always in this form. Multiply by x to get the antiderivative of any constant. So a constant like 14 is nice. And it means over here, the next part of our antiderivative is going to be 14x. And yeah, sure enough, we've said this a lot. If you differentiate 14x, you can think of this as a linear function whose slope is always 14. The derivative equals a slope, or just use the power rule. You'll get a 14 on that one. Then next term is starting to get a little bit hard to read. So let's take that box off so it's not so visually oppressive. Last term is going to be -5 times antiderivative of 1 over x. That's going to be natural log absolute value of x. Putting it in purple because that one is easy to miss, I'd say. Then last thing is to add a constant. So when we go to read this out as a check, we would be putting in -5 natural log absolute value of x plus a constant. I didn't really think that through on how much space I needed on that. There we go. With our reformatting, derivative of -5 natural log x would give us -5 times 1 over x. 1 over x is from the derivative of natural log absolute value of x. And that's our total check. But really the idea is we look into these individually. Derivative of 3x squared is a 3x. Derivative of 14, yeah, we can see that as a 14. And derivative of natural log absolute value x, yeah, it is a 1 over x. So a lot of times it's good when the problem gets big to do a mental check term by term by term. And this is just represented as a total check, differentiating all terms at once. We get 3x plus 14 minus 5 over x. That was the provided lowercase f of x once we algebraically put it in a nice format. So our work is done on this one. That's the end antiderivative. Definitely a weirder problem though. Oh, don't want to hit delete on that. But we'll move over now to try out part B, kind of a similar sort of question. And really that's what example 3 is all about. A lot of the problems in the 4.6 homework assignment are just ready to go in the antiderivatives, but plenty of the problems need extra algebraic manipulations as well, like this one. So let's try this out next, part B, to see how it goes. And really, this is, again, a very similar problem. This is something we could have had as a problem in section 3.3. Instructions would be to just differentiate, but we did problems just like these. What we'll do this time is, just because we're taking the antiderivative doesn't change the method. Either the derivative or antiderivative needs a big correction on every single one of the exponents that came in with the radical notation, the square root or the fifth root, for example. So take this f of x. We're going to do some exponent surgery on it and rewrite it as f of x equals. Also, division by 2 like this is a bit confusing for derivatives. Let's rewrite it like this. Division by 2 is multiplying by a half. Square root of x is just square root of x, but x specifically to power 1/2 is a better way to write it. On the next term, this is 2 times x to the power of. Let's really look into this. It's power 2, but I brought this up into the numerator, so I have to flip the sign to a -2. And it was a fifth root, but the root itself tells you the denominator part. So this is -2/5. So this is really kind of 3 things happening. Power 2 stays right where it is here. The fifth root means you divide by 5, but we also need to bring the whole thing up into the numerator. So instead of x to power 2 divided by 5, we change the sign to a negative in that way. So what's happening on that one? Does that make sense on tracking those steps for that second term? Okay, those are the only weird parts of this thing. So on the last bit, just directly copy in e to the x minus 9. And now we'll do term by term anti-differentiation. F of x is going to now be equal to, constant multiple rule still applies. Keep your 1/2. Here, we're going to multiply by a new value, but add a little bit of space before you write in your x. Now we're reversing the power rule right here, which means we add 1. But if x is 1/2, adding 1 means adding 2/2. If we were differentiating, we'd subtract 1, which would be minus 2/2. So add 2/2 to 1/2, and we get 3/2. We have to divide by 3/2, but what we really do is we multiply by its reciprocal, 2/3. Let's write that out as a comment. From here to here, division means multiply by the reciprocal. And you didn't necessarily have to write it that way. I'm going to bring this back to the way it was. If you wrote it this way, divide by 3/2, that is absolutely totally correct. The only downside to it is it's a big longer vertically. It's harder to write in, and you still have to simplify this stuff. It's more confusing to simplify. So instead of divide by 3/2, jump to the step where you already have to do this anyways. Multiply by the reciprocal, 2/3. Much cleaner cancellation right on this line. Less confusion going this route. So even though it's not required, I would say it's a good idea to do it that way anyways, just for the sake of accuracy and clarity. Let's do this all over again. We scoot over to the second term, go +2. Add a little bit of space. Here's x. Denominator is 5, so we go up. That means add 5/5. Negative 2/5 plus 5/5 is going to give us 3/5. We divide by the new power 3/5, which means multiply by 5/3. And that term right there should be done at that step. There's the fun terms. E to the x is a freebie. In antiderivative, it is itself. -9 is practically a freebie as well. It's a constant. And as per our last comment up here, if you find a constant, just multiply it by x to get the right antiderivative. That was 14 going to 14x. Likewise, -9 would just go to -9x. Add a constant c here, and our job is done. We have an antiderivative. We have to do some simple corrections here on the 2 cancellations, 2 times 5, to get it simplified. But this was the major work getting to this step. Let's write in now that we've gotten here. F of x is equal to 1/3 x power 3/2 plus 10/3 x to the power 3/5 plus e to the x minus 9x plus the constant c. Well, we got it, folks. This one is pretty nasty because we're doing an antiderivative, but this kind of problem as a exam 3 question, just differentiating it, it wasn't too bad for the class. You took these same type of steps to differentiate it. The only difference was use the power rule in the ordinary direction. We reversed it here, but we have one more thing to do. Let's do a full-on check. We're going to differentiate f of x, and now this is us checking if our work is really correct. Constant multiple rule says 1/3 stays exactly where it is. Ordinary power rule has us multiplying by the exponent first, so times 3/2. Power goes down by 1, subtract 2/2 for a 1/2. Rinse and repeat on this term. 10/3 times the old exponent, 3/5, times x to the power of 1 less. We're taking 3/5, subtract 5/5, so -2/5. Now the derivatives get nicer. This is e to the x. Derivative of -9 times x is -9. These always go to 0, and I'll just leave it blank here to say we knew that, we didn't have to write anything here. Then it does simplify, but because this is a check, we might not simplify it completely. I'm just going to show the cancellation. We have 1/2 x power 1/2. That is the lowercase f of x term 1. Over here, we have a cancellation going this way, leaving a 2, going that way. So it's just 2 times x power negative 2/5, directly what we had up here. The last terms are easier to check out. Either the x at -9 directly track. So we can call this lowercase f of x. And a little check here just as a reminder, that was our objective. Come up with a function that, when we differentiate, gives back this one here. Definitely a bit of an adventure on this, especially taking well-known formulas like the power rule and now using them backwards. That's what makes section 4.6 a lot more challenging. But once we get a good handle on this, it leads directly into the integration methods. Any questions or comments at all, folks? Surviving part B on this one. Okay, let's try this out again. Here's part C. It looks like the last question on these whole entire notes. So nearly done with the antiderivatives. We have another one to survive through, and this is just like what we dealt with in section 3.3. You would never want to use a product rule on this one. It works, but it's a product rule with 3 factors. It's more complicated than is necessary. If we saw this in section 3.3 and we were told to differentiate, our first job would be just to expand this function. So that's exactly what we're going to do. Expand first. So let's now rewrite f of x as, up to you how you want to expand. I think for me personally, I would usually leave the -3x right here. And then just focus on FOILing out that part. Up to you how you'd like to do it. If going this route, we'll get 3x squared minus x plus 15x minus 5. That feels like deja vu, but this one is similar to part A. Only difference was we had to divide x into the result. This time everything is multiplied, but very similar parts right here. Then it's plus natural log 4. That one isn't doing anything. It's just a constant hanging out. So f of x is now equal to -3x, 3x squared plus 14x, minus 5 plus natural log 4. Finally, you can distribute the -3x in to get negative 9x cubed plus, rather minus, that's 30, 3 by 4 is 12, so minus 42x squared plus 15x plus the natural log of 4. So now f of x in this format is far easier to differentiate, and it's far easier to find the antiderivative to, which is our objective on this problem. The antiderivative, uppercase f of x, is the function you need to differentiate to get the prior result. But here's the systematic way of getting this new function. Copy in the coefficient -9, then multiply x to 1 higher power. Power 3 goes up to power 4. I'm dividing by power 4 immediately once we find it, so now it becomes -9/4. Rinse and repeat. Next step, constant is -42. Multiplies x, the power goes up to now power 3. Take that new power 3, divide the coefficient by it, and that finalizes that step. Any questions so far, folks, with those first two terms? Okay, let's keep on going. The more systematic and methodical you can make this, the better. Try to do it essentially the same exact way each and every time. I'll always put down the constant 15. If the power is a fraction, I'd include a little bit of space because I have to multiply it by a reciprocal. But the power is not a fraction, so I'm just going to directly put x next to it. Next step, up the power by 1. It's power 1 at the red dot, so now it's power 2. Take that new power, immediately divide into coefficient in front, and you've got the right part in that step. This is the worst step right here, though. Anyone see what the antiderivative should be from natural log 4? It just feels weird when we look at these kind of expressions like this one. But my claim is we kind of know what to do. We just have to get away from the abstraction that this is just written as a weird number. The fact about this number, though, is that this is constant. If it's a constant, that means the antiderivative is no different than getting the antiderivative of, say, the 14. 14 was constant, so we just attach an x to it. Similarly over here, -9 is constant, so we attach an x as well. And natural log 4 is a weird looking constant, but it is constant just like all the others. In fact, we can really emphasize that. Plot f of x equals natural log 4. And there it is. It's constantly equal to the value of natural log 4, about a 1.38 for any x value you throw in. So that means we get natural log 4. We always multiply by x once we spot the constant. And then the last thing that's honestly easy to forget is we need the constant of integration c. If this was, say, like a 6-point exam question, that constant is worth 1 point. If you forgot it on your entire final exam, you're only going to lose a point once as just a required concept that we didn't see. You're not going to be nickeled and dimed every single time you forget it, but it is important. It's got to be there some stage. Last thing, the function does simplify, so let's simplify it. -9/4, x power 4. 3 goes into -42. Let's double check from this list. It was 3 times 14 to get -42. So this will be a -14. X cubed. 15 halves x squared. Natural log 4 times x plus a constant. A lot of rewriting to just simplify one spot where the red dot is. But we now have an antiderivative. Last thing we should do with this is put this to a test. Let's see if it's a real antiderivative. By doing the more comfortable procedure, we're really good at the check. We're shaky on coming up with the antiderivative itself. But if the check works out, we'll have good knowledge that we have the right answer here at the red dot. So we're differentiating this whole entire line. The derivative is going to be -9/4. Give it a little bit of space because upon differentiating, we multiply by the exponent right away. Then we update the exponent. We drop it by 1. It's power 3. Repeat here. This is -14 times 3, x power 2. This part is plus 15 halves times 2, x power 1. And we're taking the derivative of x power 1, just the constant survives. Natural log 4. Derivative of the arbitrary constant c goes to 0 as well. And another look on this, cancellation going this way, so -9x cubed. Checks with the -9x cubed on lowercase f of x. Over here, -14 times 3 is a -42. So we have the correct term on that one here. This one's a cancellation, but that leaves 15x upon canceling. We started with 15x, so that is correct. And the natural log part does work out as well. So this tells us this f of x in derivative equals lowercase f of x directly. So our check is complete. I'm going to remove these checks up here because that's a bit of a distraction. But finally, it tells us that is the right answer, the antiderivative f of x. Well, any questions at all, folks? Coming up with that last one here. Okay, with everything we've done on these notes, there wasn't any big application that we were really looking into. There are a couple in this section 4.6, but it leaves everything that we've done in this problem set pretty mysterious. Why did we want antiderivatives? Before we go to chapter 5, it's a good idea to answer that question. Let's do it right here. Actually, I think we can fit it in on this line right here. Let's now turn over from the tangent line problem that's solved by the derivative. The slope of a tangent line is just the value of the derivative at the right x-coordinate. But now we're turning this around to the area problem. In the area problem, you have a setup that might look something like this. Let's make this an application while we're at it. This is T for time. So we have a t-axis being a t variable for time. We'll also have a y-axis, but y is going to be equal to v at t. So this is going to be a velocity function. So velocity at time t. So here's the setup so far. The curve I'm writing out is now a curve for the velocity function. And you can imagine this is something that if you're driving a car, you can experience. The velocity function is like your speedometer at some time t after you put the car into gear and start driving forward. So velocity might look like this to start. That means the car is starting at rest. That's good. It's not starting at 5 miles per hour. You didn't chase it down to jump into it. Then let's say this person really just is really heavy on the gas and goes like this. And then we just stop tracking time right at this point. The car disappears. Who knows what happens to this car? It's just no longer here. But this is equal to y equals v at t. And let's say it goes from 0 minutes to, let's say, 2 minutes. Maybe the accelerator wasn't as heavy as we might have thought. And we went from, well, it's a velocity, so let's think in terms of miles per hour. We started at 0 miles per hour. Let's say this ended at, after 2 minutes, something like 60 miles per hour. So that's what this curve represents. Your speedometer over the course of 2 minutes going from 0 miles per hour to 60 miles per hour in this kind of way. It's an interesting graph, but the question about this graph is, what was the total distance traveled? That's a different kind of question, right? This is telling you the velocity at any moment of time. We're wondering, how much ground did you cover? How far did you go in those 2 minutes just driving forward? We do know that distance is equal to the rate times time. But our rate is tricky. It's variable, right? If the rate was always 60 miles per hour, graph might have looked like this. And that means we could have taken 60 miles per hour here. Time would be 2 minutes. Let's say hours. Let's just correct our units to make this a little bit easier picture to work with. Let's say we went for 2 hours. That would just mean, well, you went 120 miles altogether. So the area under this curve is just the rate 60 miles per hour. That's the height times the length. That's directly an area this time. In fact, the answer to this question, even if it looks like this, is still an area. Only difference is you're taking the area of a right triangle. The area would be 1/2 the length of the base times the height. But our situation is more complicated. We want this kind of area. So that's what's making it a legitimate area problem. This area, no matter what the curve looks like, represents distance traveled. So let's say it this way: area equals the distance. And this is just one version of an area problem. Essentially, anything in the sciences, if you draw its graph, the area is probably really interesting. Not just areas. Area could represent energy, it could represent power, it can represent a distance, just about any application you can think of. The area problem is a really important one that we really need to solve. But this is a hard problem to find the area under something that has a curvature like this. Not a horizontal line, not a straight line. Getting that area is not easy. This is where antiderivatives come into the mix. The antiderivatives directly solve this area problem. Here's how it does it. Let's rewrite just another graph so this last one doesn't get too busy. Here's a new graph that goes this way. Let's make this an x-axis and a y-axis. So just a generic problem this time. Similar looking function just to connect the concept. Here's y equals just a generic f of x. To get the area under this curve, here's what we've got to do. Let's call this an a value. A is 0 in this problem, but it could be any value whatsoever. This point where the function ends, where the area is tied off right there on that line, we'll call this a value b. And we can say now next that the area is going to be equal to f of b minus f of a. This equation right here is the preview to section 5.3. And it's one heck of a statement when you really look into this. It is telling us that this total area trapped under the curve in blue is simply found by finding the antiderivative of this function. Let's bake that into the problem here, where f prime of x equals lowercase f of x. We're directly finding an antiderivative. And then when we find that antiderivative, it's only relevant on the boundary values. We look into the antiderivative on one point here, another point here, and that's all that matters. The difference of f of b minus f of a is the exact area, and that's a really, really wild statement. It's such a wild statement, this is called the fundamental theorem of calculus, part 2. Interestingly, this is the second version. This is the part that was independently discovered as well by Isaac Newton and Leibniz at the same time, independently as a discovery. They were able to connect an entire branch of mathematics, differentiation, with finding area. Somehow the derivatives are extremely relevant to an area problem. In particular, we just need the antiderivative to solve this whole thing. Really, really weird and bizarre when you think about it. But let's now turn into section 5.3 to see how all this stuff kind of starts off. Any questions or comments at the moment on thinking about this problem so far? Okay, so we did a whole bunch of antiderivatives, mentioned a problem that we want to solve next in chapter 5, the area problem, and this is the direct connection. We just need an antiderivative and we're on our way. We're going to test that out, but before we do that, section 5.3 is a pretty abstract section, so it starts off just a little bit more slowly. Ooh, first, let me fix my windows here. The way Microsoft works with these panes is interesting, but it's worth it to try to work with Microsoft to get our actual white space properly configured. So finally, we're on the fundamental theorem of calculus. And what the first page is really talking about here is everything interesting in calculus, like we've mentioned before, is somehow in some way defined through a limit. That's why we spend so much time in chapter 2. Continuity, an interesting concept all on its own, is defined through a limit. So is differentiability. We're going to rewrite this limit here just as a reminder. The reason we're doing all of that is the last problem we were describing, finding the area, it really is a limit problem as well. So let's start off with this equation. The equation f prime at 3 equals 9 tells us a lot of information. On the graph of y equals f of x, at x equals 3, the tangent line has slope 9 is one thing it's telling us. But we want to write this out in the form of a limit, so let's start by putting in some extra information. From section 3.1 or section 3.2, they're very similar looking sections. We defined f prime of x to be equal to the limit as h goes to 0 of f of x plus h minus f of x all over h. And we computed with that several times as well. We did some tangent line equations in the most painful way possible by directly working with that equation down here. So that's relevant over here. If we were writing this out in the form of a limit, we would say first for this part, f prime at 3 just means we're putting 3 in for x right over here. we're looking into the limit. As h goes to 0, f at 3 plus h minus f of 3 divided by h. So that's just the f prime part. It has to be directly equal to 9. And so we're just saying the whole limit itself is 9 in that way. So that was a reminder of what we were doing in really chapter 2, leading into section 3.1, going into chapter 3. It was all about getting a good handle on that limit right here. But now that we're looking into the area problem, we have a new kind of limit. We won't do as much direct work with the new limit like we did over here, doing those tangent line equations in section 3.1. But still, it's really helpful to see how does it come together before we go to use the fundamental theorem. Any questions so far, folks, on example 1 before we go to the bigger problem? Okay, and if you're curious on this limit, because it has been a while, it's not a bad idea to go all the way back to section 3.1, just as a reminder. What that limit was trying to achieve was getting the slope of the tangent line here in blue. It was really a lot of work when you think about it. It takes a lot of work to describe what are we computing in the first place, what does it look like, and this is the diagram that made it happen. Likewise, we need a diagram that's going to help us think about how do we compute areas in the very first place so that we can relate it back to derivatives, more specifically antiderivatives. So here's our new problem that we're going to take a look into. Let's hide that definite integral part. We have a function f defined from a to b. So let's start there. I'm going to put everything pretty much in quadrants 1 and 4. Let's call this our a value. This is our b value. The function f, I'll plot in blue. Let's say it starts off positive way up here. And it's an area problem. But one thing we didn't say in the last section is it's a signed area problem. Some of the area will be positive, some of it will be negative. So going from here to here, this part is the positive area because it's above the x-axis. And this is the negative area being now below the x-axis. Let me just retarget where b is based on where the curve actually ended up. So we've got a function. Here's our y equals f of x. Coming from this part of the definition. It's defined from a to b, so we threw that down as well. And we're going to divide the interval, bracket ab, so the closed interval, into n subintervals of width delta x equals b minus a divided by n. Really, our goal here is we want equal widths in our intervals. And it's nice to see the functions defined on a closed domain. That means if our function's continuous, it'll have an absolute maximum, it'll have an absolute minimum. We don't have to worry about infinite areas anymore. There is a finite area guaranteed by this, as long as we assume f is continuous, like in the next part. So let's take this portion right here. Delta x equals b minus a divided by n. These are going to be the equal width. Intervals. And this is going to represent a partition for the closed interval from a to b, using this as the width. So we start at x naught, being the a value. Then we get x1 by moving over a distance, delta x. So from here to here, just add delta x. And we'll do that repeatedly so that the width of each next tick mark in the interval always the same. So in the next value, x2, right over here, x3 goes in this location, and b is going to represent xn. In our problem, b is x4, and the diagram we're writing down is for n equals a 4 value diagram. This part is important right here because this is a very dynamic picture. I don't know how to do this by animation. That's not part of my background. But imagine this is the n equals 4 diagram. Really what's happening is n is getting larger. Kind of like what's happening here in the limit, h going to 0, except we're taking the limit as n goes to infinity. So the equal widths then over here go to 0. And that's going to give us an exact area on the diagram below. So once we do that part, we have the endpoints of the subintervals. We now actually need test points, x1 star through xn star. Our author calls them sample points in the intervals, so that each xi is between the prior xi minus 1 and the next xi. Or in other words, our xi star could be, say, this point. It could be the far left endpoint. It could be x naught. It could be all the way here at x1, or it could be directly in the middle. I'll just draw them in generically in the middle, just for ease of writing this all out. We'll call this one x1 star. And this is what x1 star does. From right up here, we go up and we hit this height. Right at this height, we have a height f of x1 star. And let's just rinse and repeat. Find another value, x2 star, gives us a point right at this height. x3 star gives us a height below the x-axis. This is where we start getting negative values. So let's write in this one because it's interesting. We have a value below the x-axis now, f of x3 star. You know what? We might as well put them all in. If we put in a couple, it makes it weird if we didn't put in the others. Start to wonder what's wrong with f of x2 star. So let's put that in the diagram as well. So we're still getting through the sample points constrained in each one of these parts of the interval. Last one is going to be x4 star, giving us a point down below here, another negative value on the vertical axis, x4 star. So lots going on with this diagram. It gets pretty busy as we go. But remember the purpose of all this, we want area. And you can imagine how you find this area. The sample points are going to be determining the heights of approximating rectangles. So this height going left and down, going right and down, goes between the left endpoint x naught, the next point x1, and that's an area we can calculate really, really effectively. We just multiply the length and the height. Next approximate rectangle goes from here to here. And they're true approximations. Notice this one underestimates the area in this red dot, overestimates area over here where the red dot is now. There's kind of a balance between underestimating and overestimating. It's not the perfect area, it's just an approximation. But n gets large. The bigger n it gets, the narrower the widths of these go, and the error that we get starts to diminish. Recall we're taking the limits like this one, but n goes to infinity. The accuracy is only going to go up upon limiting. Here's where it gets interesting though. This one has a height below the x-axis. This is where we pick up negative area because the function value itself is a negative value. And that's what we mean by signed area. If we're thinking about a velocity problem, this is positive area right here. That's the car moving forward. This would be negative area. This is the car now moving backwards if we get negative area, if we're thinking velocity. Negative velocity means reversal of your direction. Then last one at this height goes like this, and we're about ready to put in the signed area. Area is positive up to this point, and then it becomes negative on these two. Any questions so far with what we've got on the diagram? Okay, let's write this next part out. The signed area, I'm saying signed area because there's a positive part and a negative part, is going to be equal to approximately. Now we're just looking into the areas of all these rectangles. What we would do is take the height. The height of our very first approximating rectangle is f of xi star. Then we would multiply that by the width going this way. The width is just your delta x. Then do it all over again. The next rectangle is at this height, so we'll take f of x 2 star. I should have called this one an x1 star, not an I. Let me fix the subscript on that. Indexing can definitely get a little bit wild with all these new symbols. Take f of x2 star, that's the height going this way. Then the width going this way is delta x again. And that's essentially the pattern, except that when we go here, we go plus f of x3 star times delta x. On this one, because f of x3 star is below the x-axis, we're picking up negative area. That's really weird how that does that. Let me fix my pen here. It's a weird lag that comes in occasionally with the pencil tool in this class. So this is going to be negative area. But the first function values, f of x1 star, f of x2 star, they are positive. So these two terms are going to give us positive area. Last thing to throw in there is final term plus f of x4 star. Now we're targeting that last approximating rectangle. Multiply it by delta x. So this is our approximate signed area. By what we have on the graph, we know the total area for this should be positive altogether. The positive area part has a bigger contribution. But if we let n go to infinity, this just gets better and better, and we have a nice approximation for the exact signed area. Any questions at all, folks, with the logic of getting these things down coming from over here? Okay, here's the next weird part. The thing about this expansion here is there's nothing wrong about it, except n is going to be large. We're taking the limit as it goes to infinity. So we just want a more compact way to represent repeated addition. Here's what it would look like. It's a summation formula where n starts from 1, because that's the very first index that we have here. It goes up to 4. And instead of indexing on n, let's index on I. N has a different role. We shouldn't double use it. That could be an abusive notation. So now instead of writing f of x1 star through f of x4 star, we can use the index I and just simply write f of x I star. Multiply it by delta x. So we can compact this formula a whole bunch. Essentially, all that's happening here is, again, the repeated addition part, this, and this, turns into the summations formula right here. Now, next part of this whole process is that we have to admit it's just an approximation to this stage using n equals 4. This is a limiting process just like the derivative we looked into above. So we'll say the signed area equals, and this is a nice equals. It's exact this time. No approximations, no estimations whatsoever. We want the true signed area under the blue curve. So imagine these rectangles in teal are becoming so fine because the width is going to 0, because we're taking the limit as the number of rectangles goes off to infinity. When that happens, these get so fine it starts to look like a sawtooth pattern. And then finally, it just looks like shaded area. You can't even see the width of the rectangles whatsoever. The limit is on this summation. It'll be as I goes from 1 to n. So we replace 4 here because we're letting n go up to infinity. We have to say that, so we put limit n goes to infinity and put it there. Then last thing is f of xi star times delta x. This limit is pretty hard, like we mentioned before. It's harder than doing this kind of limit that we did in fact do in section 3.1. But if we can rephrase this problem in just the right way, fundamental theorem of calculus part 2, it turns out the way you do this limit is just through the antiderivative, like we looked into on the end of the last section notes. So when we get across our review next Thursday, or potentially after the exam coming back on the 24th, it looks like, we'll finish off this problem here and show how to integrate finding signed area using the fundamental theorem. But this definitely looks like a good stopping point for us. This is abstract work. I appreciate your hard work and patience on this one. Any last questions or comments before we call it a day? Okay, well, have a great afternoon, folks. When we return next class, we'll take questions relative to exam 3, and I'm happy to spend all the class time on that if it turns out that happens. If we run out of time, we'll just return back to these notes. So come prepared. I'll be happy to work with as many questions as we discover we need to discuss.